Imagine a future where really complex problems, think critical medical diagnostics, or maybe sifting through just mountains of information, are handled not just by, advanced AI, but by AI agents.
Right.
And these aren't just smart systems. They actually learn, they adapt, they even specialize, all without you constantly telling them exactly what to do. No explicit reprogramming needed.
It sounds futuristic, but it's happening fast.
Exactly. That future, it's not some far-off sci-fi dream anymore. It's rapidly becoming our present. Welcome to the Deep Dive. This is where we unpack a stack of fascinating sources on the real cutting edge of artificial intelligence. Today, we're diving deep into the world of these AI agents. These are systems capable of making decisions on their own, carrying out multi-step tasks, and interacting dynamically with their environments.
Pretty sophisticated stuff.
Yeah. We're going to explore how they're revolutionizing fields like medical imaging and complex knowledge retrieval.
Yeah.
We'll look at what makes them so incredibly adaptive and also, what challenges and opportunities they bring up for all of us.
Sounds good.
Our mission today, pretty simple. Give you a shortcut to getting up to speed on this really transformative technology.
And it's amazing just how quickly these capabilities are moving, from the lab into the real world.
Definitely.
Our sources today, they give us a pretty wide view. We've got reports on medical imaging startups. The very latest FDA guidance literally just came out.
Oh, wow.
Yeah, and then deeper academic surveys on things like reinforcement learning from human feedback, RLHF, people call it.
RLHF, got it.
And they'll also unpack some really innovative frameworks like Memento for memory and Triad for multi-role specialization, plus the power of retrieval-augmented generation, or RAG.
RAG, okay. Lots to cover. So where do we start? I mean, what's a big problem that AI agents are uniquely suited to solve? You mentioned healthcare earlier. Maybe medical imaging?
Yeah, that's a perfect example. Think about the huge pressures on healthcare, specifically in medical imaging and radiology.
Right.
The biggest issue, perhaps, is the sheer dependency on human expertise. Traditional diagnosis relies so heavily on radiologists' experience.
Which isn't always consistent, right?
Exactly. It introduces subjectivity, variability based on, their skill level, or even just fatigue. And unfortunately, there's always the potential for human error.
And overlooked findings can have serious consequences for patients.
Devastating consequences sometimes.
Right, and the volume alone. I mean, the amount of data must be just staggering.
It is. The sheer volume of imaging data, MRIs, CTs, PET scans, ultrasound, X-rays, it's growing like crazy. It far exceeds the number of qualified radiologists we have globally.
Which leads to bottlenecks.
Huge bottlenecks, yeah. Diagnostic delays, and honestly, professional burnout among radiologists. It's a real problem. A single radiologist might be looking at hundreds of images every single day across all sorts of different modalities.
Wow. And beyond just the quantity, are there specific qualitative challenges? Are certain things just hard for humans to spot consistently?
Absolutely. Traditional methods often struggle with detecting very subtle abnormalities or early-stage diseases.
Like what, for example?
We're talking about tiny malignant tumors, maybe the earliest signs of Alzheimer's lesions, or really faint indicators of something like a pulmonary embolism.
And missing those early on.
Means delayed diagnoses and often poor treatment options down the line. Then add on the high operational costs, sometimes inconsistent image quality, which means repeat scans.
More radiation exposure for patients, too.
Right. Plus, you've got limited access to specialists, especially in rural areas. And then there's all the manual documentation, the difficulty in tracking disease progression over time. It just compounds the problem. Makes consistent quality really, really hard to achieve at scale.
Okay, that paints a really clear picture of a system under serious strain. So how do these autonomous medical imaging analysis agents step in? What's their sort of unique value here?
Their unique value is consistency and scale. These next-gen AI systems, they're designed to automatically interpret medical images with exceptional accuracy, remarkable speed, and really consistent precision across huge data sets.
So they don't get tired, basically.
They don't get tired. They don't have off days. They bring a level of consistency that human interpretation, just by its nature, struggles to maintain over long shifts or massive volumes.
That really does sound like a game changer. So what are the immediate sort of tangible benefits we're seeing or can expect very soon? How do they actually boost efficiency or accuracy in practice?
Well, the immediate benefits are pretty significant. They boost efficiency, they enhance diagnostic accuracy, and they accelerate decision-making quite dramatically.
Can you give an example?
Sure.
Yeah.
Think about an AI agent reviewing hundreds of chest x-rays overnight. It could flag any suspicious lung nodules, so when the radiologist comes in the next morning, those cases are already prioritized.
Okay, that makes sense.
Or maybe it enhances a blurry MRI image in real time, potentially saving the need for a repeat scan. That reduces patient inconvenience, saves money, improves the whole experience.
And we're actually seeing this happen now, right? You mentioned real-world examples earlier.
Precisely. Take FFITPU Healthcare from Singapore. They have developed something called Midalytics. It's an oncology imaging analytics platform.
What does it do?
It performs a quantitative assessment of tissue microvascularity, basically blood flow in cancerous tumors. It supports different imaging types and can even spot microcirculation issues in stroke events.
So it gives doctors objective data fast.
Exactly. It empowers them to make timely, accurate clinical decisions, potentially improving patient outcomes significantly. It's about getting data that was previously very hard or very slow to obtain.
And I imagine the impact goes way beyond just that one application, like helping in underserved areas.
Definitely. These agents can provide preliminary AI interpretations in rural or remote places, then send the annotated results to specialists elsewhere. They can do highly specialized analysis too, like for cardiovascular imaging, quantitative metrics, 3D reconstructions for heart conditions.
Wow.
They can even adapt protocols for pediatric imaging, accounting for age differences. And beyond diagnostics, think about standardizing imaging in clinical trials or using dashboards to optimize radiology department workflows.
Tailored reports?
Yes, tailored insight packages for different subspecialties, oncology, neurology, including even prognostic forecasts, exploring what-if treatment scenarios.
Okay, back to that FDA guidance you mentioned. That feels like a pretty big deal, right? Almost like an official stamp of approval. Does that change things for adoption?
It absolutely does. The fact that the FDA issued final guidance on PCCP, streamlining FDA approval for AI-enabled medical devices, and just yesterday, August 28th, 2025, that sends a really clear signal.
A clear regulatory path.
Exactly. That's crucial for building trust and speeding up adoption. It provides a framework for safety and efficacy, moving these innovations from just promising research into tools that can actually be deployed in clinics.
Okay, so these agents have incredible capabilities. How do they actually learn to do all this? Not like someone programs every single rule, right? What's the magic sauce?
Well, a core method, and one we mentioned earlier, is reinforcement learning from human feedback. RLHF.
RLHF, right. How does that differ from, say, traditional AI training?
Unlike traditional AI that often relies on, carefully engineered reward functions, basically telling the AI exactly what earns points, RLHF lets the AI system learn directly from human input.
From our feedback.
Yes. It's this really fascinating intersection of AI and human-computer interaction. The goal is to align the AI's objectives with human values, but in a much more nuanced way.
That feels like a pretty fundamental shift. So how does that RLHF cycle actually work? Can you walk us through it?
Sure. It typically happens in two main phases. First, there's reward learning. In this phase, the agent basically learns an approximation of a reward function, but it learns it from human feedback. So the system might generate queries, maybe pairs of different AI outputs, or different ways it tried to do something.
But showing us two options.
Exactly. And then it collects human labels, our preferences, critiques, comparisons between those options.
Okay, so it learns what we prefer. Then what?
Then comes the second phase, RL training. The agent uses that learned reward function, the one based on our preferences, to train its own policy, its own way of behaving. It continually refines its actions based on what it learned we think is good.
So it's learning the reward signal from us instead of having it pre-programmed.
Precisely. And separating these two phases has practical benefits. Like, you can use standard supervised learning for the reward model evaluated on its own. But the real power is that RLHF lets the AI learn what good looks like from our, often subtle preferences. It moves beyond rigid rules to align with us more naturally. It's not just about getting the AI to do something, but to sort of understand our values implicitly.
That makes a lot of sense. Human preferences aren't usually just a simple number. So how do we actually give this feedback? What forms does it take?
Well, there are several types. Critique is probably the most direct. A human watches what the AI does and labels it, maybe just good or bad. It could be explicit feedback, or maybe even interpreting like Physiological signals, brain activity, perhaps?
Wow, really?
Potentially, yeah. Then you have comparisons. This is very common. Humans compare two or more options, like two different responses that AI generated, and say which one they prefer.
That seems easier than giving an absolute score.
It often is. It helps reduce bias, too. You can extend it to ranking multiple options as well.
And you mentioned natural language feedback, too.
Yes, and that's incredibly versatile. Humans can just type out their preferences, suggest specific changes, describe what they want the AI to do, all in plain English, right in the context of what the AI just did.
But using humans also introduces challenges, right? Like, what if different people prefer different things?
That's a big one, especially with crowdsourcing. People's preferences might conflict. Researchers are trying different things, learning individual preferences, finding a sort of collective mean preference, maybe even using more complex multimodal reward functions.
Sounds tricky. And are there issues with the reward system itself sometimes? I think I read about something called reward collapse in LLMs.
Ah, yes, that's a significant issue. With large language models, sometimes the way they're trained using rankings can lead to this reward collapse. Basically, the reward signal flattens out and becomes uniform, no matter what the input prompt was.
So it stops learning effectively.
Pretty much. It highlights the need for more sophisticated ways to measure utility, ways that take the prompt itself into account. And this leads to another challenge: query quality.
Meaning what questions to ask the human.
Exactly. You want to ask about the most informative examples, the ones the AI is most uncertain about. That's where active learning strategies come in, intelligently picking the best queries for human review. But crucially, these queries also need to be simple enough for humans to actually answer. You don't want weird, unnatural comparisons, especially when the agent is just starting out and might be doing really odd things.
Okay, so learning from feedback is key. But you also mentioned Memento. What if an agent could learn continuously from its experience without needing that constant, expensive fine-tuning of its core model? That seems like a huge advantage.
That is precisely the groundbreaking idea behind frameworks like Memento. It tackles that exact challenge by giving the AI agent a kind of adaptive, evolving memory.
Adaptive memory, how does
Yes.
that work? It uses something called case-based reasoning, or CBR.
That's right, within a planner executor setup. The agent maintains what's called a case bank. Think of it as a growing memory of past experiences or cases.
What's in a case?
Each case typically includes the situation the agent was in, the state, the action it took, and the reward it got. So when the agent encounters a new situation, it searches this case bank for relevant past experiences.
And uses those past experiences to decide what to do now.
Exactly. That retrieved experience guides its planning and then its execution of actions. But here's the really clever part. Instead of changing the underlying LLM's parameters,
Which is the expensive part.
right, Memento refines a separate parametric Q function. That's basically a model that learns to estimate how good an action is in a given state based on the rewards seen in those past state case pairs.
So it learns the value of recalling certain past experiences in new situations.
Precisely. It allows the agent to adapt and improve over time, essentially learning from experience, but without modifying its core LLM. The learning becomes much simpler, often more like supervised learning, avoiding tricky issues with non-stationary targets.
It's like having a dynamic playbook based on past results, but keeping the core engine stable.
Yeah.
Clever. And it uses external tools, too.
Yes, to stay up to date and make better decisions. For instance, it might use a self-hosted meta search engine like SearXNG that pulls from Google, Bing, DuckDuckGo as a sort of coarse filter.
To get a general idea.
Yeah, and then for more detail, it might use web crawlers like Crawl4AI to fetch and parse the full content of relevant web pages. That's the fine-grained information.
So with this memory bank, does bigger always mean better? Just keep adding more and more cases.
You'd think so, but interestingly, the research suggests otherwise. It seems a small, high-quality memory is actually more beneficial than a massive one that might just introduce noise or slow things down.
Quality over quantity again.
It seems so. And another, perhaps counterintuitive finding, sometimes faster, less deliberative planners can actually outperform more complex, slow-thinking ones for certain tasks.
So quick retrieval of the right memory might be better than mulling over everything.
In some contexts, yes. Efficiency and relevance seem key, not just sheer memory size or processing depth.
Okay, so Memento gives agents memory. What about specialization? Can we build agents that work like a team, each handling a specific part of a complex problem?
Absolutely. That's where frameworks like Triad come in. Our sources introduce Triad as a system that uses a multi-role LLM-based agent specifically to tackle knowledge-based question answering KBQA.
KBQA, that's like asking questions of a huge structured database, right?
Exactly. Think querying something like Wikidata or Google's Knowledge Graph. Triad approaches this by assigning different roles to different aspects of the agent.
It's like a specialized research team. What are the roles?
There are three main ones. First, the generalist agent, or G agent. This one is good at mastering various smaller subtasks, mainly by learning from examples.
What kind of subtasks?
For instance, generating Sparkula templates. Sparkula is like SQL, but for these knowledge graphs. And a key finding here, echoing the Memento point, is that the quality of the examples you give the G agent matters way more than the sheer quantity.
Quality over quantity again. Okay, who's next?
Next is the decision maker agent, the D agent. This agent is all about identifying options and picking the best ones.
So filtering and selecting.
Yes. In KBQA, it might filter potential entities or relationships from the vast knowledge base, use the LLM to choose the most likely ones, construct the actual SPEM-RQL queries, and then pick the most plausible query from a list, maybe even throwing out queries that don't return any results.
And you mentioned something surprising here too.
Yeah, interestingly, having too many candidate options for the D agent to sift through can sometimes actually hurt the overall performance. Again, maybe suggesting that strategic selection is better than just throwing everything at it.
Fascinating. And the third role?
That's the advisor agent, or A agent. This one provides the comprehensive final answer. It draws on its own internal knowledge, but also the results retrieved from the external knowledge bases via the queries. It also acts as a kind of fallback if the initial queries don't quite hit the mark.
So they all work together?
Cooperatively, yes, handling the whole KDQA process in 4 phases. Parsing the question, linking terms to the knowledge base, URI linking, constructing the query, and generating the final answer. And this triad framework, it's been shown to outperform traditional KBQA systems on standard benchmarks. Really highlights the power of specialized collaborative AI agents.
Okay, so Triad gives us specialized teams, Memento gives us memory, incredibly powerful combinations. But we still had that lingering issue with even the best LLMs sometimes, making things up, hallucinating, or just giving outdated information.
Right, the grounding problem.
How do our agents deal with that? This feels like the perfect job for retrieval augmented generation RA.
That's precisely it. RAG is a really promising way to tackle those challenges. It works by integrating the LLM with external dynamic knowledge bases.
So it's not just relying on what the LM learned during its initial training?
Exactly. The real genius of RAG isn't just feeding more data, it's about creating this connection to an always up-to-date, verifiable knowledge source. This dramatically reduces hallucinations and grounds the AI's responses in actual, current, accessible information.
It's like giving the LLM a super-powered, always-on research librarian.
That's a great analogy, yeah.
So how does this RAG pipeline actually work in practice? What are the steps?
It's a pretty clear pipeline. First is indexing. You take your raw data PDFs, web articles, whatever, clean it up, break it into smaller, manageable chunks. Then you encode these chunks into numerical vector representations, like coordinates in a high-dimensional space.
Embeddings.
Embeddings, yes. And store those in a specialized vector database. That's step 1.
Okay, index the external knowledge, then what?
Then comes retrieval. When a user asks a question, that query also gets converted into a vector. The system then performs a similarity search in the vector database to find the POP-K, the most relevant chunks of text based on the query vector.
Finds the closest matches in that vector space.
Correct. Finally, there's augmentation. These retrieved chunks, the most relevant pieces of external knowledge, are provided as extra context to the LLM along with the original query.
Ah, so you're giving the LLM the relevant background reading before it answers.
Precisely. It directly guides the LLM's generation process, steering it towards an answer that's grounded in that retrieved information. It's like an open book exam, where the system flags the most relevant pages for the LLM.
Makes sense. And I gather RAG itself is evolving. There are more advanced techniques now.
Oh, absolutely. Beyond that basic pipeline, advanced RAG is really pushing the envelope. You have things like pre-retrieval optimization.
What's that involve?
That could mean refining how the data is indexed, maybe optimizing the chunk size, adding metadata, or it could mean improving the user's original query, rewriting it, expanding it to make the retrieval more effective before you even search.
Smart. Getting better results by asking a better question, essentially.
Exactly. Then there's context curation and re-ranking. Sometimes you retrieve a lot of chunks, and maybe they're redundant, or the most important bit gets buried in the middle. LLMs sometimes suffer from this lost in the middle problem. They pay more attention to the start and end of long texts.
So re-ranking helps.
Yes, re-ranking reorders the retrieved chunks to put the most relevant ones first. It acts as both an enhancer and a filter, improving focus.
And what about making the retrieval itself smarter, not just a one-shot search?
Right, that's intelligent retrieval. It can be iterative, where the system searches the knowledge base multiple times using the initial query and maybe the text generated so far to refine the search and gather more context.
Or recursive.
Recursive retrieval is where the search queries themselves are refined based on previous search results. It creates this feedback loop, honing in on the best information, especially for really complex or ambiguous questions.
And even autonomous searching.
Yeah, that's the cutting edge. Systems like WebGPT use reinforcement learning to actually browse and search the web autonomously. And things like Self-RAG use special reflection tokens. The model can basically pause, reflect on its own output, and decide if it needs to go retrieve more information based on its own competence level.
Wow. It's learning when it needs to look things up.
Pretty much.
Okay, so we've got these incredibly powerful agents learning, remembering, specializing, accessing external knowledge. With all this rapid progress, how are the humans in the loop actually reacting? Let's circle back to radiology, for example. What are the doctors thinking?
Well, a survey of radiology residents actually showed widespread enthusiasm, which might be surprising to some.
Really?
Yeah, 74% saw AI as beneficial, 95% wanted more AI education in their training, and almost 89% believe AI will drastically change radiology. Yet, interestingly, 80% would still choose the specialty today.
So they see it coming, they want to learn about it, and they're not necessarily scared off by it.
Largely, yes. But there's a gap. About 65% consider themselves AI or machine learning novices. And nearly 60% reported they weren't getting enough AI education in their residency programs.
So there's a clear need for more training to integrate this into the medical curriculum properly.
Absolutely. It highlights a definite need to bridge that knowledge gap, make sure future professionals are really prepared to work with these tools effectively.
That's a fascinating mix. High enthusiasm, but also a recognized need for more learning. What about AI's actual performance in these medical settings? Is it living up to the hype? Is it replacing humans or more complementing them?
The studies show a mixed picture, but generally it leans towards complementary right now.
Yeah.
For instance, AI could generate medical multiple choice questions that matched human quality and do it faster. GPT-4 consistently did better than GPT 3.5 on some orthopedic exams. That's promising. But another study looked at an AI system helping detect things on chest x-rays. It improved residents' performance, but only while they were using it. When they stopped using the AI assist, their performance went back to their baseline.
So it helped in the moment, but didn't necessarily transfer skills long term.
In that specific study, yes. However, in surgical training, AI-based metrics for robotic performance correlated very highly with human expert observations and often outperformed the residents' own self-assessments.
So it could be a really objective assessment tool there.
Potentially, yes.
So connecting this back to the bigger picture, it really sounds like AI's role, at least for now, is often as a very powerful assistant or maybe a tool for objective measurement rather than a full replacement for human expertise, especially when things get really nuanced or the stakes are super high.
That seems to be the consensus from the current evidence, yes. And as these AI agents get more and more sophisticated, learning from our feedback, remembering past experiences, taking on specialized roles, using external knowledge, it naturally raises really important questions.
Like trust, accountability.
Exactly. Trust, accountability, ethical deployment, that FDA guidance we talked about, that's a critical step in building a framework for responsible integration, especially in sensitive areas like healthcare, making sure these powerful tools are used wisely, effectively, and, alongside human professionals.
What an incredible journey through this landscape. We've covered so much ground, from AI agents tackling huge challenges in medical imaging to the nuts and bolts of RLHF, the memory boost from Memento, specialized teams in Triad, and grounding it all with RGA. These systems are truly changing how we handle information and solve complex problems. They're constantly learning, constantly adapting.
It really makes you think, doesn't it? As these AI agents become more autonomous, learning, remembering, adapting, all without explicit human reprogramming, what does that really mean for human expertise, for our own learning processes? And here's a final thought. If AI can learn effectively from human feedback and potentially even learn from other AI, There's this emerging concept called RLAIF, reinforcement learning from AI feedback.
Wow, AI teaching AI.
Potentially. How do we make sure that human values, our ethical considerations, remain absolutely central to this continuously evolving intelligence? Especially when the teacher providing the feedback might also be artificial. It definitely leaves you with a lot to chew on about our future, living and working alongside these increasingly intelligent partners.